Yes, hi dear students. So today let us continue our discussions related to the Gauss law as well as its application. So in our last video we studied the proof of the Gauss law as well as its statement. So today we have to move on to the applications of Gauss law. So actually we have three applications of Gauss law, but one application has been included under the deleted portion. So we have to study the two applications. If we want to learn or if we want to derive the applications of Gauss law, we have to follow some common steps in it. So before that, we should know once again recall the Gauss law as well as we must know the concept of Gaussian surface. Yes, as we already know that the Gauss law, it is going to give the concept of the total flux associated with the closed body enclosing some charge, where we are going to write that the flux phi is equals to q upon epsilon naught. Phi is equals to q upon epsilon naught. So the last states that the total flux of a closed surface is equals to 1 by epsilon naught times the total charge enclosed by that surface. 1 by epsilon naught times the total charge enclosed by the surface. And this Gauss law is applicable for closed surfaces for what kind of a shape or for what may be the kind of distribution. Either it may be linear charge distribution, surface charge distribution, volume charge distribution. Irrespective of the type of the distribution, it is applicable, but it is applicable for closed surfaces. So we have to remember the steps we have to follow to get the applications of the Gauss law. We have to derive the very important two applications. One is the electric field due to uniformly charged infinitely long wire. So if we think of the wire, we have to think of the distribution of the charge, isn't it? So in case of wire, out of the linear charge distribution, surface charge distribution, volume charge distribution, we can easily think of the charge distribution. So the first step we have to remember while deriving the applications of the Gauss law is to know about the distribution of the charge. After knowing the distribution of the charge, we should select the Gaussian surface such that it should be a closed surface. It should enclose some of the charge, isn't it? Then next to the selection of the Gauss law, we have to find the total flux associated with that Gaussian surface. That is our third step. So after selecting the Gaussian surface, we have to find the total flux associated with our respective Gaussian surface. So next we have to make use of the Gauss law, and finally we have to find the electric field expression. The electric field expression. Okay, so these are some of the steps we should remember for easily remembering the applications of Gauss law derivation. So first we have to think of the distribution of the charge. Next we should think of the selection of the Gaussian surface. Next we have to find the total flux associated with the Gaussian surface. Then we have to make use of the Gauss law, and finally we have to find the expression for electric field with respect to the respective distribution of charges. Okay. Yes. So now let us move on to the first derivation, that is electric field due to uniformly charged infinitely long wire. Electric field due to uniformly charged infinitely long wire. Long wire. Yes. So this is very important. So we have to think of the distribution of the charge. They have clearly mentioned that is for wire. So I am going to consider a wire. Yes. It may be of infinite length and the distribution of charge with respect to the wire, that should be along its length. So it is having linear charge distribution. So the distribution of the charges here, that is along its length, so we can consider it is linear charge distribution. Yes, with respect to this wire, now we are thinking of the distribution, that is linear charge distribution. So we can have the total charge, and next to the total charge we have to think of the Gaussian surface, and we have to choose a point P, which is an arbitrary point where we have to find the electric field with respect to this distribution. So yes, we came to know about the distribution of charge, and now we have to think of the Gaussian surface. So for this we are going to select the cylindrical Gaussian surface. Here the Gaussian surface we are selecting, that is the cylindrical Gaussian surface, which is enclosing certain portion of the wire, which is having the linear charge distribution. So with respect to this Gaussian surface, and here we have a positively charges associated with that. So this is the direction of the electric field, and choose some arbitrary point P, which is at a distance r from the wire, and at that arbitrary point we have to find the electric field. Okay. Yes. So let us just consider this is a wire, and this wire will be having the Gaussian surface, that is somehow the cylindrical Gaussian surface. Yes. I am going to consider this is the cylindrical Gaussian surface which encloses the given wire. Or we can consider this is a wire and this is a cylindrical surface, and this cylindrical surface is enclosing the wire. Yes, like this. So now we have to find electric field at some point P, which is at a distance r from the wire. So in order to find the electric field, we should find the total flux associated with this cylindrical surface. If we want to think of the flux, we have to recall the formula of the flux, where we have phi is equals to E A cos theta, where E is the electric field, A is the area vector, and the theta is the angle between the electric field and the area vector. So already we have discussed all these things in detail. So here for this cylinder, we are going to have three surface areas. One is the cylindrical surface area, the other one is the upper surface area, the lower surface area. So here totally we have three regions. So now out of these three regions, where the flux will be 0 and where the flux will be not equal to 0, that depends on the angle between the electric field and the area vector. And already we know that the area vector is always normal to the given surface area. Therefore, so let us consider we have three surfaces, that is the curved surface, the upper surface as well as the lower surface for a given cylinder. So with respect to this, now we are going to consider the flux. So first I am going to write the charge. So the total charge here we can consider the linear charge distribution. Lambda is equals to Q divided by L, which implies Q is equals to lambda into L. Q is equals to lambda into L. Yes, we got the total charge, and we consider the Gaussian surface. So with respect to the top surface as well as the bottom surface, the area vector and the electric field, they are perpendicular to each other. Yeah, this is the top surface. The area vector will be normal. That means it is acting vertically upwards, and electric field is in forward direction. It will be like this. Area vector with respect to the top surface is upwards. The electric field will be in forward direction. So the angle between the area vector and electric field becomes 90, and cos 90 is equals to 0. In the same way, for the lower surface, the area vector is vertically downwards, the electric field is in forward direction. So at the lower surface also we have the theta value as 90, so cos 90 becomes 0. So the entire flux for this given Gaussian surface, that is because of the curved surface, where we have this curved surface and area vector will be like this. So we have the curved surface and area vector will be in normal direction, isn't it? So what is the direction of electric field? That is forward. What is the direction of area vector? That is also in forward direction. Or we can say the electric field and area vector for the curved surface, they are in same direction. Then the total flux we can consider phi is equals to, yes, so I am going to consider the entire cylindrical surface. Just initially we are considering the small surface area, right? That is delta. Yes, so delta S will be the small surface area and E is the electric field and area vector and electric field are in the same direction. Therefore, the total flux phi is equals to summation of E into delta S. Summation of E into delta S cos theta. And for curved surface, theta is equals to 0. Therefore, cos 0 is equals to 1. What about the remaining? The top surface and the bottom surface? With respect to the top surface and the bottom surface, the flux becomes 0 because of 90 degree between the electric field and the area vector. So we just left with the electric field because of the electric field because of the curved surface, the electric flux because of the curved surface. So the total flux phi is equals to summation of E into delta S cos theta and theta is equals to 0. So cos 0 is equals to 1. Therefore we have phi is equals to summation of E into delta S. Phi is equals to summation of E into delta S. So the total electric field, it will be taken as E only. So summation of delta S. Here at point B we have a small surface area. As we want to find the entire flux with respect to this cylindrical surface, this summation delta S will become the surface of the cylinder. That is the total flux associated with the curved surface. So now phi is equals to E into, yes, so this is the surface area of the cylinder and we know that the total surface area of the cylinder is given by 2 pi r into L, where L is the length of the cylindrical surface. Where L is the length of the cylindrical surface. So the total flux we got phi is equals to E into 2 pi r L. Yes, that completes the total flux concept. And now after finding the total flux, we have to make use of the Gauss law. So by Gauss law, we know that phi is equals to Q upon epsilon. So let us call this as equation number 1 and this is equation number 2. So by equating equation 1 and 2, because we have flux in both the equations, so if RHS is same, we can equate the LHS. So by equating equation 1 and 2, we can write E into 2 pi RL is equals to Q upon epsilon. And we can have the total charge Q as lambda into L. Therefore, E into 2 pi RL is equals to, what is Q? There is nothing but lambda into L upon epsilon naught. So this L on both sides will get cancelled. Our intention is to find the expression for electric field. So electric field E is equals to lambda divided by, so 2 pi will be taken to denominator, 2 pi r epsilon naught. Electric field E is equals to lambda divided by 2 pi r epsilon naught, where lambda is a linear charge distribution. And we know that electric field, it is a vector quantity, so we can represent this in the form of the vector. Vector E is equals to lambda by 2 pi r epsilon naught into r cap, where r cap is a unit vector along the direction of electric field. So it's very simple derivation. Yes, quickly we can recall the things. So here we are considering the infinitely long uniformly charged wire, where the distribution of the charge is linear charge distribution. So the total charge Q is equals to lambda into L. So next we have to find the flux by selecting the Gaussian surface. So here we are considering the cylindrical Gaussian surface enclosing some portion of the wire. Therefore, we have totally three surfaces. The flux due to the first and second surface will be 0 because theta will be equals to 90 degree, and only the flux exists because of the curved surface where theta is equals to 0. Therefore, the total flux associated with the curved surface of the cylinder is phi is equals to summation of E into delta S cos theta, where we are finding the electric field at point P, which is at a distance of r from the wire. Then theta is equals to 0, cos 0 is equals to 1. So we left with phi is equals to summation of E into delta S. So electric field will be E, and summation of delta S. We have to find the total surface area of the cylinder. So the total surface area of the cylinder is 2 pi r into L. So we got the total flux of the curved surface phi is equals to E into 2 pi r L. So next we have to make use of the Gauss law. So by Gauss law we have phi is equals to Q by epsilon naught. So equate the equation 1 and 2, and finally we got the expression for electric field E is equals to lambda by 2 pi r epsilon naught. And vectorially we are just writing vector E is equals to lambda by 2 pi r epsilon naught into r cap. So this is the first application of Gauss law. Now we have to move on to the second application of Gauss law, where we have to find the electric field due to uniformly charged infinite plane sheet. Uniformly charged infinite plane sheet. The same steps we have to follow. Yes. Instead of wire, we have to consider the sheet. So, I am going to consider the diagram. So here we have the uniformly charged infinite plane sheet. Yes. So there will be some sheet like this. Yes, it is a sheet where the distribution of charges is uniform. So now we have to find the electric field because of the distribution of the charges over its surface. So we have to follow the same steps. So we have to first think of the distribution of the charge. So here we have the plane sheet, means the distribution of the charges over on its area. So it is surface charge distribution. So let us consider the surface charge distribution. So we have that sigma is equals to the surface charge distribution, that is sigma is equals to Q divided by A. Sigma is equals to Q divided by A. Then the total charge Q is equals to sigma into A. The total charge Q is equals to sigma into A. Now we have to select the Gaussian surface. So here also we are selecting the cylindrical Gaussian surface. It will be like this. So if this is a sheet, the cylindrical Gaussian surface will be selected like this. So it is enclosing some portion of the sheet. The cylindrical Gaussian surface will be selected. So just I am going to represent that with the diagram. Okay. So are we clear? Yes. This is the cylindrical surface and this is a sheet. So it is enclosing some portion. It will be like this. It will be like this. So here we have the Gaussian surface, that is a cylindrical surface. So now here the cylindrical surface once again has the three surfaces, 1, 2 and 3. Now the cross sectional area of that cylindrical surfaces, here it is A and here it is A. The horizontally mounted, the curved surface will have the area vector upwards and the electric field, that is outwards. So the angle between that area vector and electric field will become 90 degree. But with respect to these two surfaces, so this is the direction of electric field and that will be the direction of area vector. So you can consider the flux associated with this, that is phi is equals to E into A, the flux associated with this surface is phi is equals to E into A. So after finding the charge, now we have to move on to the total flux associated with the Gaussian surface. So the total flux phi is equals to, we can call this one as a phi 1 and this as phi 2. That is phi 1 plus phi 2. Phi 1 plus phi 2. So phi is equals to E into A plus E into A. It becomes 2 EA. It becomes 2 EA. So you got the total flux. Next we have to make use of the Gauss law. We have phi is equals to Q upon epsilon. So this is equation 1 and this is equation 2. What next? Just we have to compare the equation 1 and 2. If you compare the equation 1 and 2, we are going to get 2 EA is equals to Q upon epsilon. And here the total charge Q will be replaced by sigma into A. So we have got 2 EA is equals to Q is nothing but sigma into A by epsilon. So A on both sides will get cancel. Our intention is here to find the expression for electric field due to uniformly charged infinite plane sheet. Therefore the electric field E is equals to what happens? Sigma will be as it is, that 2 will be taken to the denominator. So E is equals to sigma by 2 epsilon naught. So this is the expression for electric field due to uniformly charged plane sheet. Uniformly charged infinite long plane sheet. Okay, very simple derivation, right? So first we have to consider the distribution of the charge, and we got Q is equals to sigma into A. And if we observe the Gaussian surface, here it is a cylindrical surface. So the first and the third surfaces will have non-zero flux, and the curved surface will have a zero flux because theta becomes 90 with respect to the curved surface. So the curved surfaces will be yes, so normal, that is area vector will be normal. And here the electric field direction, it will be outwards. So upwards is the outwards is the angle between them becomes 90, so flux becomes 0. So here the flux will be because of the first surface and the second surface where the electric field is A and the surface area is, the electric field is E and the surface area is A. So phi 1 is equals to EA, and for third surface also we have phi 2 is equals to EA. The total flux phi is equals to phi 1 plus phi 2. We got phi is equals to 2 EA. That is equation number 1. So now after that we have to consider Gauss law. That is by Gauss law phi is equals to Q by epsilon. That is equation number 2. And we got 2 EA is equals to Q by epsilon, where Q is sigma into A. And finally we got the expression for electric field. That is sigma by 2 epsilon naught, where sigma is the surface charge distribution or surface charge density. And the third application we have, that is the electric field due to uniformly charged spherical shell, but that is not required. So please practice the two important applications of the Gauss law, that is electric field due to uniformly charged infinitely long wire and electric field due to uniformly charged infinite plane sheet. Okay? Yes. So observe the numerical. A uniform charged sphere of 2.4 meter diameter has a surface charge density 80 microcoulomb per meter square. Find the charge on the sphere and the total electric flux leaving the surface. So they are asking to find the total charge and the total electric flux. If we focus on the given data, here it is a charged sphere and the diameter they have provided d is equals to 2.4 meter, and it has a charge density, that is the surface charge density sigma is equals to 80 into 10 power minus 6 coulomb per meter square. Coulomb per meter square. They were asking to find the total charge, that is Q is equals to question mark, and they were asking to find the total flux, isn't it? So we have to find the total charge and we have to find the total flux. So the distribution of charge here is surface charge distribution. So we can consider sigma is equals to Q upon A. Sigma is equals to Q upon A. Therefore, which implies the total charge Q is equals to sigma into A. That is sigma into A. So what is A? That is surface area of the sphere, that is 4 pi r square. So here we have to find the total charge. Q is equals to sigma into 4 pi r square. What is sigma value? They only provided the sigma value as 80 into 10 power minus 6. So here we have 4 into 3.14 into, what is the radius value? It will be 1.2 meter, isn't it? Diameter is 2.4, then radius will be 1.2, that is 1.2 square. So the total charge Q will be equals to, yes, please make use of the calculators. So we are going to get the total charge as 1.44 into 10 power minus 3 coulomb. 1.44 into 10 power minus 3 coulomb. So after finding the total charge, they were asking to find the total flux. Yes, by Gauss law we have phi is equals to Q by epsilon. What is Q value? Yes, we got that Q value as 1.44 into 10 power minus 3. And we know that epsilon naught is 8.854 into 10 power minus 12. So 1.44 into 10 power minus 3 divided by 8.854 into 10 power minus 12. Then the flux phi, we are going to get it as 1.62 into 10 power 8 Newton per coulomb meter square. Phi is equals to 1.62 into 10 power 8 Newton per coulomb meter square. Like this, we have to solve the numericals related to the Gauss law and applications of Gauss law.